Here's another video for the lecture Intro PDE. In this lecture we present the second half of section 3.4, Green's function. In the first part of section 3.4 we introduced the concept of Green's function and explained how to solve Dirichlet's problem with Green's function. At the end we determined the Green's function of the unit ball. Here is the formula. So this is the formula for the Green's function of the unit ball. And now we want to show that we can really solve Dirichlet's problem with this Green's function. So we finish in this section this program in the case of balls. Okay, here is the statement. This is Poisson's representation formula. So what is the assumption? We have a twice continuously function which extends to on any ball. We have given any ball of radius r around z in Rn. And we have given a function f which is twice continuously differentiable on the ball and such that the function and all partial derivatives up to second order extend continuously to the boundary of the ball, so to the closure of the ball. And we have a continuous function on the boundary of this ball. Then the unique solution of the Dirichlet problem is given by this formula. So this is a complete formula for the solution of the Dirichlet problem. Now let's recall why this solution is unique. This we explained in the first half. This is a direct consequence of the weak maximum principle, because the difference of any two solutions of this Dirichlet problem, the difference is harmonic, because both have the same inhomogeneity, so the difference on the right hand side is 0, so it's harmonic, and it vanishes on the boundary. And then by the weak maximum principle we know that the difference itself vanishes, so both functions are equal. This is the uniqueness. Now we prove the existence. Now let's prove the existence. Okay, proof of Poisson's representation formula. Okay, first we observe that we may prove both cases, g equals 0 and f equals 0 separately. Since everything is linear, we might first take this integral, and then we should obtain the solution which corresponds to g equals 0, and this integral should give the solution to the case when f is 0. Also, the first integral gives should give, maybe I should say, should give the solution for g equals 0, because then this term vanishes, and the second integral should give the solution for f equals 0. So we can prove both cases separately. Okay, now now first let's prove that now we claim that the Green's function to this ball of xy is just equal to r to the n2 minus n times the Green's function of the unit ball, which we determined, and then evaluated at x minus z over r and y minus z over r. Okay, why this is the case? Now, if we look for the map, x going over to x minus z over r, this maps, of course, the ball with radius r around z onto the unit ball. Now this is clear. If here the difference to z divided by r, also if the difference to z is smaller than r, then this here is smaller than 1. Yeah, and clearly this is the inverse map. Inverse map is, yeah, this is easy. Now if we try to we want to solve this for x, then we have x goes over to r times x, r times x plus z. Yeah, and both maps are smooth. Yeah, both maps are smooth. Smooth, so it's a diffeomorphism. Yeah, so these maps are diffeomorphisms. Okay, and they map this to this, and of course also the boundary of ZR onto the boundary of the unit ball. This is clear. If the distance of x to z is r, then here this has absolute has length 1. Yeah. Okay. So this is easy. Yeah. So and there now we claim as a first we observe that if we multiply this difference minus this, yeah, if we multiply this by this constant, yeah, then just by this definition, this function here we claim vanishes, yeah, because okay, clearly this only depends on the difference. So for the difference, the set cancels, yeah. If we bring this is of course, yeah, x minus z over r minus y minus z over r is of course equal to x minus y. Sorry, x minus y. X minus y. X minus y over r. Okay, and now if we multiply the argument in phi with 1 over r, yeah, then by the definition of the of this function, sorry, I won't show it to you. Yeah, what do we get? Yeah, here I have to recall the fundamental solution. So here it's the fundamental solution. So if we multiply this by r, yeah, then we only get, of course, in factor r to the n minus 2 in the bottom, yeah, for n not equal to 2. And for n equal to 2, we just get an additive term. So this really shows this statement here. Yeah, so we really have that that this difference vanishes for n larger than 2, and for n equals to 2 it's constant. So this implies, yeah, that if we multiply Green's function and we parameterize the arguments, that then clearly this vanishes on the boundary of this ball, this function considered as an x, yeah, because this clearly vanishes on the ball, and this doesn't change this property. And the first property was that the difference to this function, yeah, is harmonic. Yeah, constant function is harmonic. Yeah, so this also follows. So this immediately follows now from our definition, from these two properties. Yeah, the Green's function gives this. So this proves the claim. Yeah, this proves the claim. Okay, so we determined Green's function. Now let's consider the case. G equals 0. Yeah. Now first, for G equals 0, now we remember in theorem 3.2 we observed that if we write here, if we write in the representation formula here the function phi instead of the Green's function, yeah, then we obtain a solution of the Poisson's equation. Yeah? But this function differs from the function phi just by an harmonic function. Okay, we should be careful. First, we showed this only independence of y, but due to the symmetry, this is also true if we consider this as a function of x. Yeah, this is by the symmetry. This is harmonic, and yeah, if we consider this as a function on x, this is harmonic. No, sorry, this we don't need, but we know by the second property that it extends continuously to the closure of the ball and vanishes at the boundary. So if x approaches the boundary, then this vanishes by the symmetry of Green's function. Yeah, so really ux, yeah, by symmetry of the Green's function, u of x vanishes at the boundary. Okay, so the first property we have now, it should solve the Poisson equation. Yeah, the difference vanishes. Therefore, the Green's function. Yes. So now by the first property. Yeah, by the first property, the function u differs by a harmonic function from a solution of Poisson's equation. Yeah. Okay. One should keep in mind that both the Green's functions and phi are both symmetric. So this is not only the case, yeah, this property is not only the case for as the function depending on y, it's also the case as a function depending on x. Yeah, so we really see that this differs from a solution of the Poisson equation by a harmonic function. Yeah, and solves Poisson's equation on the ball. Yeah, this proves the statement for g equals 0. Now we consider this situation f equals 0. Then we only get the second term. Yeah, so we only get the second term. Okay, and now here for this we should keep in mind, yeah, we should keep in mind that by this formula here we should expect that we just have to take this integral here. So let's calculate this, the negative of this expression. Yeah? This we will calculate now. Yeah. Okay. So here we calculate the negative of this of the gradient of this Green's functions multiplied with the normal. Yeah. So with the normal, if y belongs to the unit ball, then this is the outer normal. Yeah. Outer normal of 0, 1 is y divided. Okay, at y. Okay, yeah, this is clear. Okay, so we calculate this. Now, keep in mind that we already once calculated the derivative, yeah, divergence of y, of x minus y. Yeah, this we calculated. We get. Well, okay, maybe I do it again because it's translated here. Yeah, so this is square root of x minus y square. So we get inner derivative is clearly 2 times x minus y, or maybe y minus x, and so this is the square root of this term, and to simplify, we write this. Of course, here the square is independent, so this is, of course, sorry, here is missing something. Here we need, sorry, I write this again. Yeah, so this is gradient of square root of x minus y square, of course multiplied as a scalar product of the vector with itself. And this is, of course, gradient of square root of y minus x square. So if we do now the calculation, then inner function is 2 times, yeah, this. So we get, this is 2 times y minus x divided by 1/2 is the square root y minus x. Yeah, so this formula, yeah, we obtain, so this is y minus x over y minus x absolute value. Okay, now the outer function is clearly this to the power of 2 minus n. So we multiply by 2 minus n. This cancels with this and this minus. Yeah, so here and here we both have this exponents, so we cancel this. Yeah, here the same is of course true if we replace x by x tilde. Okay, so we and the outer function is we have to diminish by 1, so we get n minus 1, and then together with this factor we get a power of n. Yeah, so the divergence of this term just gives this, yeah, by the chain rule and this calculation. And here, okay, here we have written that x absolute value, also the length of x to the power of n minus 2 is of course the same as here, this divided by absolute value square. Okay, so we have written this in this form. So we get this expression here. Yeah, this is just simple calculation of the divergence. Now we call with this, we have seen in the last section. Sorry. Yeah, we have seen that this expression here is the same as this expression. So the absolute value, so x absolute value, yeah, x times x tilde minus y is the same as x minus y. Sorry. For this is equal to 1. Now we use this, yeah, because we calculate this only for this. So if we insert this, then we know here the bottom terms are equal. So we can bring it on this form here and write this term here. Now this is of course 1, so we can neglect it. Yeah, by our assumption it's 1, so we can neglect it. And then what we get here, we get y squared. Y squared is of course 1 by this assumption. Then we get minus x times y, or y times x. And then we get the last term is, these are these two terms here. Then what we get here, y times y is of course 1 again. So we get minus x absolute value square. Then y times x tilde is of course defined as x by x squared. So x squared times y times x tilde is of course the same as y times x. Yeah, so we get, and here we have a minus is a plus, so we get plus this term. And then we see this to cancel and this terms remain. So we calculated now this term, and now we just insert it in our formula which we already know. Okay, now very important, in the first part we derived a nice formula. Yeah, we derived a nice formula here. This formula, we derived this formula for the Green's function. In general, this formula holds. If we insert u equals 1 in this formula, then we have 1 is equal. Now all derivatives of 1 of a constant are 0. So this is equal to, and this we call, this is now k. So we recall this is with the minus equal 1 k of x, y, and this scalar product is already k, by definition, with this minus d sigma of y. So this holds here, this equation holds. Yeah, we showed this for all x in the unit ball. Yeah, this follows by this formula. Yeah, so okay, now we use this. Okay, now we observe 3 properties. Yeah. Okay, what we need to show is that this extends continuously to the boundary. Yeah, we already know it's harmonic. This function here is harmonic, since this function is harmonic. Yeah, since it's a derivative of the Green's function is harmonic. Yeah, and so it's harmonic, so it solves. It's harmonic on U, on the unique ball. This already is clear. So it remains to show that it extends continuously to the boundary and coincides there with this function. Yeah, this is what we need to show. Now we observe three properties. Clearly, this is positive. Yeah, for x, y in this. Yeah, because x squared is of course smaller than 1. Yeah, we call this formula for here. This is the formula. So it's positive if x is on the ball. Okay. Second, this function converges uniformly to 0 if if lambda goes to 1, yeah, because 1 minus x squared goes to 0 for x absolute value going to 1. This is clear. Yeah, and if we have an argument x on the unit ball and then multiplied by some lambda which goes for, then we know that this goes to 0. Now look at this is the on the top the term, and on the bottom the term, this is this term here. Okay, we have to be careful, of course, if y this is bounded as long as x minus y is bounded away from 0. So we just assume that these two arguments, yeah, that we go in the complement of the epsilon ball of x, yeah, for all epsilon. Yeah, if we go to this complement, then here this bottom term is bounded from below, so 1 divided by is bounded from above. So we see that this really converges to 0 in this limit. And now this was this consequence which we already showed. Yeah? We have this here, so we have these three properties. And now we claim that these three properties, yeah, they guarantee that in the limit, when lambda goes to 1, that this function converges on the ball uniformly to G. Okay, why this is the case? Yeah, why this is the case? If we look for this integral, also integral of ball 1, we have a function on depending on y times gxy d sigma of y. And now we look at this function, independence lambda of x, and lambda converges to 0. Now we may split this integral. This integral is of course equal to the integral over the boundary of 1 minus epsilon ball around x. Yeah, g of y, k of lambda x, y, d sigma of y, plus integral, and the rest, b of 0, 1. No, sorry, now we take the rest, so we take the ball. So we take b, the boundary of 0, 1 intersecting with the epsilon ball. Okay, and then g of y, k of lambda x, y, d sigma y. Okay, and then we want to subtract So we want to subtract. Okay, now we have this. And now we take the difference. Yeah, we do the same thing for the difference. So we calculate. Also first observe, by this property, this goes to 0 for lambda going to 1. Yeah, and x on this ball. So this goes uniformly to 0. Yeah, so this goes to 0, and this we may estimate. Yeah, we may estimate since on this, if we have if epsilon is very small, then g of y minus g of x is of course very small. Yeah, okay, so and by the first property we also observe the following: 0, 1, g of y lambda x y d sigma of y minus g of x, an absolute value, is of course the same. Yeah, by the, since this integral is 1, we may put this in. Yeah, this we have done already several times. G of y minus g of x times k of x y, lambda y, d sigma of y. Okay. So, and now this is smaller if we just replace this by the absolute value. This becomes very small. Yeah, this becomes very small. So we may estimate this. Yeah, as if we take this unit ball here. Yeah, so we may estimate the second part. Yeah, we may estimate this part here. Yeah, observe that this is positive. So we may estimate this intersecting with the epsilon ball around x. And this becomes very small. So we take the supremum of y in this part, of g of y minus g of x, and times integral over b0 intersecting with b of x epsilon k lambda x y d sigma of y. Now this is not positive, yeah, so we have this estimate, and this is smaller or equal to 1 by the first property. So it's smaller or equal to the supremum of g of y minus g of x, where epsilon belongs to the ball 0, 1 boundary intersecting with the epsilon ball. Okay, in the limit, this goes to 0 for epsilon going to 0. Yeah, so we indeed see that this approaches that this goes for lambda equal to 1. This really goes to 0. Yeah. Okay. So this proves that this proves now the second statement, and in this way we really prove Poisson's representation formula. Now this has some nice consequences. Yeah. First consequence is what is the first consequence of the Poisson representation formula? If u is a function, is a harmonic function on the ball, which extends continuously to the boundary, then we clearly have only the first term, so we have this formula. So this means harmonic functions on omega, for harmonic functions on omega, the values at some ball B set R inside of omega, where we assume that the boundary also belongs to omega, are determined at x, are completely determined by the values at the boundary, at the values for x in the boundary of this ball. So we may recover any harmonic function in the inside of any ball just by the values on the boundary of the ball. Now, since this function here is analytic, clearly, so the function x going over to 1 divided by x minus y is for y on the boundary. Here we take this, we have rewritten this on the boundary of set R, analytic in x in the inside, in the interior. Now, of course, here this part, the only point where this absolute value is might be not analytic is the point when x is equal to y, but this cannot happen if x belongs to the inside of the ball and y is on the boundary. So it's analytic. So we can represent it, we have convergent power series. And this now implies by this formula that u is analytic in this ball. And this means every harmonic function on an open domain is analytic. Now we have really that any harmonic function, so this means for harmonic functions the weakest regularity, so it is harmonic distributions, have automatic the strongest regularity, have in the interior of the domain, so inside, not at the boundary, the strongest regularity, it is, this means they are analytic. This is really very strong statement. Okay, now finally we also prove an extension theory. That a bounded harmonic function which is harmonic on a punctured domain. Yeah, so we have here some domain omega, and we have one point sitting in omega, and we say that omega if it's harmonic on omega without any point 0, any point x0. Yeah, of course here by a translation we may shift this point to 0. Yeah, so this is not a restriction. So if it's harmonic here and bounded, yeah, locally, of course this might be bounded in any neighborhood of x0, then it extends as a harmonic function. Yeah, now this proof is very nice. So we use on a ball with compact closure in we have this formula. Yeah, so we define U tilde, the unique harmonic function in the inside. So we choose a ball and define U tilde in this ball B of 0 r. Oh, sorry, x0. I should write, yeah. Which is harmonic in the inside and so in harmonic, and U tilde is equal to U on the boundary. We know that this exists. We constructed this solution of the Dirichlet problem. And now we will prove, we claim that U is equal to U tilde on Bx0 R without 0, of course, because at 0 U is not defined. But U tilde is, yeah, but U is not defined. So this is what we have to prove, yeah, because then we know U extends by U tilde to a harmonic function. So this is what we prove. Now we introduce this function here, this function. And then observe, yeah, that G of B, the Green's function, of x0 is for small x absolute values is positive and becomes arbitrarily large. Why is this the case? This is a direct consequence of the properties of the Green's function. Yeah? Since the difference to our fundamental solution is harmonic, this means locally it's bounded. Yeah? The difference, yeah? This follows since GB of 0R minus phi of x0 minus phi of x is harmonic and locally bounded. And since phi is positive, phi of x is positive and becomes arbitrarily large for small. Okay, this is definition of Green's function, and this is just a property of the fundamental solution. Yeah? The fundamental solution was minus logarithm of x, of course, becomes arbitrarily large for very small x, absolute values of x, and otherwise it's an inverse power of x, and then this is also true. So this just follows from the fundamental properties of the fundamental solution. Now I claim that this function for all epsilon yeah, for all positive epsilon, this function cannot take a negative values, because if this has a negative value, yeah, then we know at the boundary, at the boundary of the ball, u epsilon vanishes. This is clear, yeah, because the difference is 0, and this vanishes at the boundary, yeah, by the symmetry of Green's functions and the property of Green's function. So this vanishes at the boundary, and this vanishes, so this vanishes. And at zero, yeah, u epsilon becomes arbitrarily large. So if it's has a negative value in the inside, then it has to have a minimum, yeah, has a negative minimum if it's anywhere negative, yeah. So, but this cannot be, because then it has to be constant, yeah, by the strong maximum principle, yeah. Yeah, so this is excluded. So we have u epsilon is larger or equal to 0 for all epsilon larger than 0. And now the same argument shows that for negative epsilon, this is of course very negative, yeah, so we obtain also the argument, and u epsilon is smaller or equal 0 for all epsilon smaller than 0. Now we take the limit, yeah, so for x in the ball of 0r without, of course, the center. So then the limit of u epsilon, now we claim that for this we have u of x minus u tilde of x, or minus u of x. We look at this function, yeah. So then it's larger or equal to epsilon minus epsilon of g of okay, this is negative, but it's at this point it's bounded. Yeah, so in the limit epsilon goes to 0, then we obtain minus u of x is larger or equal to 0. And for negative epsilon, yeah, okay, here we should take the positive epsilons, and now u tilde of x minus u of x is smaller or equal to minus epsilon gb of 0 r x 0. Now for negative epsilon, here this we have for epsilon larger than 0, and this we have for epsilon smaller than 0. Again the limit epsilon, but now from below going to 0, we have minus u of x is smaller equals. So this implies u tilde of x is equal to u of x for all x in the ball 0, 1 without 0. Yeah. And this proves the claim. Yeah, this proves the claim. Yeah, so, okay. We see, if we look carefully at the proof, we see we proved a stronger statement. Yeah, because the only thing which we need is that the function, yeah, the thing what we need is that we get that if we approach to 0, if we have a negative value and then go to 0, that if we go to 0, the function, this function u epsilon becomes in any case positive. So this is enough if this function is smaller than all these functions. Yeah? So in this sense we get this stronger statement. Okay, this finishes section 3.4. Let's recall what we have done. Yeah, we in the last part we determined Green's function on the unit ball, so we derived now Poisson's representation formula. So we carried out this program which we explained how to obtain solutions of the Dirichlet problem if we know the Green's functions. Yeah, and we carried out this completely for any ball. Okay, then we had nice consequences. First, all harmonic functions are analytic, and some extension theory that a bounded harmonic function on a punctured domain extends to an harmonic function. Thank you.